Good morning, everyone. This is Sirichandana from CSCF. Today, this is about data structures. My roll number 24951A05BN. Today, I'm going to talk about community-aware graph signal processing. That is, modularity defines new ways of processing graph signals. Introduction to community-aware graph signal processing. Graph signal processing extends classical signal processing to data defined on regular structures like graphs. Community aware GSP incorporates community structures within graphs to enhance processing techniques. This presentation explores how modularity influences new methods for processing graph signals effectively. What is graph signal? Graph signal processing is an extension of traditional signal processing to data on graphs. A graph signal assigns a value to each node of a graph. That is example social network. Each user's activity score is a signal. Sensor network. Temperature at each sensor node is a signal. GSP, that is graph signal processing, uses graph structure, that is edges and weights, to process signals for filtering, denoising, sampling, etc. Basics of graph signal processing. Graph signal processing GSP involves analyzing signals that are indexed by graph nodes, capturing complex relationships. Traditional GSP methods often assume uniform signal behavior across the graph. Incorporating community structures enables more nuanced and context aware signal analysis. Understanding graph communities and modularity. Communities are groups of nodes with dense internal connections and sparse external links. Modularity is a measure that quantifies the strength of community structures within a graph. High modularity indicates well defined communities, which are crucial for community aware processing. Significance of modularity in graph. Next is significance of modularity in graph analysis. That is, graph modularity helps identify meaningful groupings that can inform signal processing strategies. Leveraging community structures improves the robustness of graph based algorithms. Modularity driven approaches can reveal hidden patterns not apparent through traditional methods. Why community awareness in GSP? Many real world graphs, that is social biological communication, have community structure. A community is equals to a cluster of nodes densely connected internally but loosely connected to other communities. Traditional GSP uses spectral methods, that is Laplacian eigenbases, which capture global structure but may ignore community level patterns. Community aware GSP, that is a community aware graph signal processing, introduces processing techniques that respect modularity, that is the quality of partitioning nodes into communities. What is modularity? Modularity measures how well a network is divided into communities. Next is significance of modularity in graph analysis. See, modularity helps identify meaningful groupings that can inform signal processing strategies. Leveraging communities structures improves the robustness of graph-based algorithms. Modularity driven approaches can reveal hidden patterns not apparent through traditional methods. Limitations of traditional graph signal processing. Conventional methods often overlook the underlying community structure of graphs. Ignoring communities can lead to suboptimal filtering and denoising outcomes. There is a need for techniques that explicitly incorporate modularity into the processing pipeline. Community aware signal processing framework. A framework that considers community structures enhances the interpretability of signals. It involves defining community based transforms and filters aligned with modularity. This approach allows for localized processing that respects community boundaries. Modularity. Next is modularity based graph Fourier transform. The traditional graph Fourier transform decomposes signals into graph frequency components. Incorporating modularity leads to a community aware GFT, that is graph Fourier transform, reflecting community structures. This transforms signals in a way that emphasize community related features. Next is community driven filtering techniques. Filtering can be tailored to reinforce or suppress signals within specific communities. Modularity based filters improve denoising by preserving community specific information. These techniques offer more precise control over the manipulation of graph signals, enhancing signal denoising with modularity. Denoising benefits from understanding community hardness boundaries to prevent signal distortion. Community aware methods adapt filtering parameters based on community strength. Results demonstrate improved signal fidelity compared to traditional methods. Next is community aware signal clustering. Clustering leverages community structures to group similar signals. Modularity guided clustering enhances the detection of signal patterns. This approach is useful in applications like anomaly modularity guided clustering enhances the detection of signal patterns. This approach is useful in applications like anomaly detection and segmentation. Next is applications in social networks. Community aware GSP analyzes user behavior within social groups. Modularity helps identify influential communities and their signal dynamics. Applications include targeted marketing and misinformation spread analysis. Applications in sensor networks. Sensor data often exhibits community structures based on physical proximity. Modularity informed processing improves anomaly detection and environmental monitoring. Community aware techniques enable localized and efficient data analysis. Applications in brain connectivity analysis. Brain regions form functional communities with distinct signal patterns. Modularity based GSP offers insights into neural activity and disease states. This approach supports more accurate brain network modeling and diagnostics. Benefits of modularity driven processing. Incorporating community information leads to more accurate and meaningful analysis. It enhances interpretability by aligning with natural groupings in data. Modular approaches are adaptable to various graph based signal processing tasks. Challenges in community aware GSP. Identifying optimal community partitions remains computationally challenging. Balancing community detection accuracy with processing efficiency is complex. Integrating modularity seamlessly into existing GSP frameworks requires further research. Next is how modularity defines new GSP methods. Instead of only using the Laplacian eigenvectors, which are global, we adapt filters to community structure, that is, process signals differently in different communities. Next is define community based Fourier transforms, graph filters with modularity priors. Next is sampling strategies based on communities. Uh, they are also applicable in recommendation systems, that is community based signal prediction, and also brain networks, that is processing signal respecting functional brain regions. Advantages over traditional GSPs. It captures mesoscale structure, that is the community level, not just local, that is edges or global entire graph. Better performance when signals are piecewise smooth inside communities but not across them. Most interpretable results for clustered networks. Challenges in community aware GSPR. Identifying optical community partitions remains computationally challenging. Balancing community detection accuracy with processing efficiency is complex. Integrating modularity seamlessly into existing GSP frameworks requires further research. Future directions in community aware GSP. developing scalable algorithms for large scale community detection, exploring adaptive methods that dynamically update community structures, extending modularity based techniques to multi-layer and temporal graphs. The summary of key concepts is modularity provides a powerful measure for understanding community structures and graphs. Community aware GSP leverages modularity to improve signal analysis and processing. The integration of communities enhances the robustness and interpretability of graph signals. Conclusion is incorporating community structures advances the state of the art in graph signal processing. Modularity defined processing opens new avenues for research and practical applications. Continued exploration will lead to more adaptive and intelligent graph based systems. Thank you.